This tutorial is about solving ordinary differential equations using numerical methods, and in this one we will use Euler's method to solve the problem of exponential growth. Now, exponential growth is given by a differential equation dp by dt is equal to lambda p, where lambda is the growth or decay constant. So in the given problem, we have initial count of 1000 and a decay rate of -2. So negative sign indicates it's a decay. A positive number will be indicating a growth. And we need to determine its growth or decay every 0.5 time intervals. This could be even millions of years in case some radioactive material is decaying. If we implement using the Euler's method that we have described here above, we get an equation pi plus 1 is equal to pi minus 2pi delta t. So if we need to implement this, we can use the same approach. We have a lambda, which is -2, and we have the initial condition at t is equal to 0, p0 is 1000. And again, we have our time domain, and in this case, we're going to go to 2 units of time at an interval of 0.1. And we have 20 in total time steps. And again, we create our empty array first, which is size 20. And again, its initial value is given here. Similarly for p, we have initial value of 1000, and all the subsequent values will be computed using the numerical approach. And again, just like the previous method, we will go from 2 to n, and we'll use our first condition to find all the subsequent values. And I have put plus here because we have already put negative with the lambda in implementation of the Euler's equation. And I've also put here exact solution in case you need to compare it with the exact solution. But for now, we will just use the numerically computed a solution. And then for visualization, we again plot all the previous point as dots and the current point as a red circle. And we create a domain axis, which is going from 0 to tn, which is 0 to 2 seconds, or not seconds, but 2 time intervals, time units, and then 0 to p0, which is the y-axis limit. And then we pause for about half second between the plottings. So if we run it, you can see how the exponential decay will happen. Okay, so this is giving us every 0.1 second. You can change it to 0.5 to see that it will have a little bit different path, because depending upon the time interval, we get different error values. So now let's go back here and put the exact value as well. And we know that there's an exact solution for this exponential growth, which is p is initial value 1000 times e to the power lambda t. So that's exactly what we have implemented here. Initial value times exponent of lambda t, but t is the current time, which is tn. So, and then this is pe, which is plotted as green axis. And we rerun this, and you can see how there's an error between the numerical value and the exact solution in case of exponential dynamics. One other thing is, let's say it was a growth, and in that case, let's say the growth rate was 1, or leave it 2. And then let's say our initial count is 10, and of course this is to be plotted from 0 to 1000, and we need to change it to maybe 500, and let's run it. So in this case, it starts from 10, and it has a growth constant of 2, and it slowly goes up, and exact value is also plotted to compare how in case of exponential growth, the error continues to increase, because at every time step there is some error which kind of starts to blow up as time progresses. Um, so we already have exponential growth, and on top of that we have error which is also growing with time.